So today we're going to be learning about Gaussian elimination. Now, the whole aspect of what Gaussian elimination is a process of which we solve a multivariable system using linear algebra. Now, the way to set up a system to be eliminated or to use Gaussian elimination on is to first take two equations and make sure all the variables are lined up in the same order in both equations, and make sure the equal signs are also lined up in the same position in both of the equations. So if I look at the two examples, I put both my x's on the left, along with the y's, and in the same order, x, then y. We took all of our constants and moved them to the other side of the equation. This, if I convert this into a matrix, gives me an x column, a y column, and then they equal our constants. Now, what we've abbreviated here is we didn't actually include the two variables, but this process doesn't necessitate us to include the two variable matrix right after there. And then furthermore, we go ahead and we augment the matrix by taking our two separate matrices and combining them into one singular matrix. And the process of Gaussian elimination follows this general form. We take our diagonal, which is where all of our pivots are located, and reduce them all down to 1. And then we take any values outside of that diagonal, any non-pivot, and we zero those out. We basically ignore what happens in the other matrix, the augmented portion of our matrix, and they will eventually produce our answers. But we don't pay too much attention. We only do work to the inside, and what happens on the outside just happens to occur. So on the front half of what we've got going on here, we have a couple steps that are going to be getting us ready for a full Gaussian elimination problem. Now, what it's going to ask us is state the row operation that we need to do first, the element that needs to be addressed, and then how many steps remain to solve the matrix as it currently stands. So let's go ahead and take a look at a few of these. So for the first one, we're going to look at our diagonal. So let's go ahead and let's highlight this. So in our diagonal, I have the numbers 1 and 6. And the way that we approach these is we approach them from the left as we go down. So my first diagonal, or my first row, is going to be good because everything leading up to and including my pivot is exactly the way it should. If I move down one, I notice that leading up to my pivot, I have a term that needs to be canceled out. So my attention is going to be on this number 3. So as far as A, B, and C go, A asks for row operations, B asks what element we need to address, and C asks for how many steps remain. Well, if I know how many steps remain, I need to address the 3, then the 6, and then I'll go back up here to address the 1. So I know 3 steps are left. The second thing I also know is that with the number 3, I know this is going to be element row 2, column 1. This lets us know that all of our attention is on the second row, the first column. So it's going to be on this entry, this number, this part right here. A is going to be the most difficult part, and it's really not too bad because we've seen this before. What row operation would take care of the 3? Well, I know that I'm going to have to get rid of something in row 2, so I'm going to set up a rule for row 2 specifically. And I'm going to say, hey, row 2, if I look directly above there, I would take 3 ones to get rid of that 3. So I'm going to say row 2 minus 3 of row 1. Awesome, and that's all we really need to do on this. Any other 2x2 matrix, we do the same thing. I'm going to take the same process, and I am going to highlight our diagonal. Those are all our pivot numbers. And as we go down from the top left, we notice that my first entry right here needs to be addressed. So for A, B, I'm going to move C down here. I know my first entry needs to be addressed, so it's going to be element 1, 1. First row, first column is where my attention goes. I also know that with that, that means there's going to be 4 full steps left. So 4 steps left. The quote-unquote difficult part is figuring out how to reduce a 5 into a 1. We know that we need to make a rule for row 1. And now where you might be tempted to use the second row to cancel out the first, the convention is to go ahead and say, I'm going to multiply by the reciprocal. 1/5 of row 1 I take 5 and flip it into a 1/5, and that will reduce that 5 into a 1. Boom. And there we go. You might have some questions as to how would I work a larger matrix. Well, this one right here is a 3 by 3. It's the same process. I'm going to highlight my diagonal and say, okay, I'm going to work my way going down. So I'm going to say, first row, everything leading up to my diagonal, including my pivots, should be zeroed out. My pivot should be a 1. That checks off. Everything leading up to the pivot is a 0. The pivot itself is a 1. And then when I check my third row, everything leading up to the pivot is not a 0. So the first thing I run into is going to be a 6. So I know out of A, B, and C, I know how to answer B and C, because at this point, I'm dealing with an element from row 3, column 2. I also know that means there will be 1, 2, 3, 4 steps remaining. Actually, 1, 2, 3, 4, and then the 5th, which is what we're about to work on. Okay. The rule that we have to come up with to cancel out the 6, well, it's going to be row 3. So I'm going to take row 3, and because it's a positive number, I'm going to take away one of these ones above it. And now I could take away the 2, but if I use the 2 to cancel out the 6, I would also have a 1 over here, which would turn my leading 0 into something that's no longer a 0, which means I need to repeat work that I've already done. So I'm not going to go all the way up to the top. I'm just going to go 1 up. And I'm going to go from the 6 to the 1 and say, how many of these 1s does it take to cancel out the 6? Well, 6 of them. So I'm at a 6 of the row above it. Awesome. Now if we pop off to something like this on number 7, what we see is that everything on the left of our diagonal is zeroed out, and all of our pivots within the diagonal are all reduced down to 1. So my first row is good, my second row is good, and my third row is good. So you're going to ask yourself, how do I move from here? Well, we just move back up in the same fashion. I move up, up, and over. In essence, if I looked at this, I would look at it from the same process. I'd look at my top, I'd go down a row, and I'd go down a row, and I'd go from outside in, which means I'm going to address this 4 first. So if we look at it from the right side, it just means that we work our way back up, kind of like working your way around a clock. So the 4 is the thing that I need to address. So out of A, actually with these we have a little bit more room to do, let's do B and C over here. Okay, so for B I need to address the element. Well, this is an element in row 1, column 3. I also know that there are only 2 steps left. The quote-unquote difficult part is figuring out how to cancel out the 4. So row 1 needs a rule. So I'm going to take row 1 and I'm going to subtract something below it. And I'm going to look directly below it, a 0. No matter how many values of 0 I take, I can't use that 0 to get rid of the 4. I'm going to have to go down 2 rows. Now, the good thing about moving down 2 rows at this point is that everything else is zeroed out. So no matter how many of these I take away, it's not going to affect anything else within this matrix. So let's go ahead and take away 4 of row 3. And there we go. So let's move on to another one. Now, the process is the same in every single one of these. As we work our way through, we just highlight our diagonal, we find the first thing going down that's out of place, and we address it. I know for this one, I can start out with saying, okay, row 3 needs to be addressed, and I'm going to take row 3 minus 2 of the thing above it, because I'm looking directly above. 2 of these will cancel out that. Most of the time, you're looking all the way into your pivot. So if I say this is going to be element 3, 2, and there are 1, 2, 3, 4, 5 steps left, you'll notice each one of these problems deals with going into the pivot to cancel out the next part. So if I have something like this, and I'm addressing the 3, again, I'm looking upwards into the pivot and saying, hey, how many of those will it take to cancel out? Well, for row 3, it'll take row 3 minus 3 of those. from row 2 to cancel out. For B, I'm addressing element row 3, 2, and C, that would mean 1, 2, 3, 4, 5 steps left. Perfect. So some of these are pretty straightforward. Just take your pivot, find the first thing. And again, remember, when we're canceling something out, we're looking into the pivot. When I'm looking in the diagonal itself at the pivot, I just multiply by the reciprocal. So for A, I'm going to take row 1, and the reciprocal of 70 is 1 over 70 of row 1. For B, I'm saying I'm looking at element 1, 1, and for C, that means that in this particular case, there are 9 steps left. There's a little bit of writing going on in this one. And so when we get to some of the larger matrices, the question you might ask yourself is, okay, if I'm looking at a large matrix like this, can I do multiple things at once? And sometimes the answer is yes, you can. So the first thing that I would do is I would go ahead and I would cancel out this 4, and then I would try and cancel out this 9. Now this one I'm going to have to do it piece by piece because the 7 right here will need to be addressed. But if I have something like this above, I can cancel out all 3 of these non-leads in one go. I can subtract 7 of row 4, I can add row 3, and take away 2 of row 2 all at once and cancel out all 3 of these. The big part is because I'm dealing 3 times over here, I'm going to have to pay attention to what's going on with this 15. But we can combine multiple steps, and eventually we'll get to the point where we're doing multiple steps. But for the most part, what we're going to be doing here is just single part, 1 step at a time. And now for step A, I'm going to take row 4 and replace it with row 4, leading all the way up into my pivot, which means I skip a row and then get into there, plus 4 of row 2. For B, I'm looking at element 4, 2. And for C, I know that means there's 1, 2, 3, 4, 5, 6, 7, 8, 9 steps left. Awesome. And so that being said, the front gave us a good idea of how we need to look at the problem. Where do we start? It's going to lead us into doing the full process. So what we've got going on right here on number 17 is how do I start a problem using a 2-variable matrix or a 2-variable system? How do I use Gauss on this? Okay, well, let's go ahead and set this up to be ready for Gauss. Now, with a Gaussian system, what I'm going to look at is I'm going to look at all my terms at this point are lined up quite well. And what I'm going to do is I'm going to take the coefficients. Now, the coefficient of my x is just going to be a 1. The coefficient of my next x is 2. And then I have 5 and 4, 26 and 22. So I'm going to create a system using those values right here. So I have 1, 2, 5, 4, 26, and 22. Awesome. And so then I just go through the process of solving this matrix, which we've just done several times. No matter where we are in the problem, I'm going to highlight my diagonal and say, hey, what's the first thing I see that needs to be addressed? Well, how about the 2? Okay. Well, if the 2 needs to be addressed, I'm going to say, how about let's take, I should have left some space down there, so I'm going to draw my, let's say row 2. Is going to be replaced with row 2 minus 2 of row 1, because I'm always looking up or down into my pivot, which is going to make these values right here. Let's leave some space. I'm just going to draw another arrow saying, hey, I'm taking that and plugging it into this matrix. Because normally what I would do is I'd write them beneath there and then write the new matrix off to the side. In which case I just exacerbated my problem. I should have written that whole matrix up a little higher and just said, cool. But the top of the matrix is unchanged, 1, 5, 26. The only thing that we have changed is going to be the bottom. So if I take row 2 and subtract 2 of row 1, minus 2 ones is going to give me 0. Minus 2 5s, that's minus 10, is going to give me negative 6. Minus 2 26s is going to be minus 52, which is negative 30. Awesome. And so my next step would be to say, okay, let's go ahead and let's highlight our line of pivots again. I'm addressing this one, which means that I'm just going to go ahead and write into my next block here. Row 2 is replaced with row 2 times the reciprocal, which is negative 1, 6, or 1 over negative 6. Now that is going to affect our second row. At this point, I should have learned my lesson. Let's scoot this up a little higher. So again, my top row remains unchanged. My bottom row is negative 1/6 of itself. Negative 1/6 of 0 is 0. 1. Negative 1/6 of 30 is 5. Okay. And then for my last step, highlight my diagonal. Everything to the left and all my pivots are good. I'm going to address the thing on the right leading up. So I'm going to say, hey, row 1 needs to be fixed. Let's take row 1 and subtract 5 of the thing below it, because that's where my nearest pivot is. So that's going to lead me to a nice new row 1. Row 2 this time is the unaffected one, 0, 1, and 5. My new values are take away 5 zeros, take away 5 ones, take away 5 fives, which is minus 25. Boom. And here we go. Now at this point, we have created the identity matrix in the right part of my augment. So we're happy. How do we interpret that as our final answer? Well, if we remember how we set up the matrix at the beginning, we have x columns and y columns and constants. So 1 and 2 were the coefficients in front of our x's, 5 and 4 were the coefficients in front of our y's. If we interpret this as a full equation, what this is telling us is that 1x plus 0y equals 1, and 0x plus 1y equals 5. But an easier way to interpret this is just to say, well, you know what? We won't normally write the zeros, and we don't normally write the ones, so that's saying x is equal to 1, and y is equal to 5. Boom. That's all you have to do to solve the system. So let's try another one, but a little faster paced. Let's try number 19. So our first step is rewrite this as a matrix, which I know that I'm going to augment this because everything's already lined up and ready to go, and turn this into a 6, 3, 12, 3, 6, 9 matrix. And I left room beneath it so I can write my row operations here. Highlight my pivots in my diagonal, and lo and behold, I've got 4 steps to go here because my first pivot doesn't work. So I know row 1, when I reduce, now I could try and reduce from below, but again, that's not the standard fashion. I'm just gonna multiply this by the reciprocal of 6, which is 1/6, which means that my top row is gonna be the changing one. 1/6 of 6 is 1, 1/6 of 12 is 2, and 1/6 of 6 is 1. Everything else stays the same. And then I rinse and repeat. I say, okay, take my diagonal, find the first thing that needs to be addressed. In this case, it's the 3. And I'm going to look up into the pivot to cancel it out. So row 2 is going to be row 2 minus 3 of row 1. Okay. So take away 3 ones, 0. Take away 3 2s, well, let's take away 6. That's going to leave me with a negative 3. Take away 3 ones, let's take away 3, leaves me with a 6. The top row remains unaffected. Awesome. I highlight my diagonal line of pivots. I find the first thing that needs to be addressed. It's in my diagonal, which means that I'm going to multiply by the reciprocal. Reciprocal of -3 is 1/3, or 1 over -3. Which means that -1/3 of 0, -1/3 of -3, -1/3 of 6. Top row is unaffected. Awesome. And so my last step right here, take this, everything leading up to my diagonals and my pivots from the left works. Now I'm looking at it from the right-hand side. So row 1 is going to be replaced with row 1 minus 2 of row 2. Take away 2 zeros, take away 2 1s, take away 2 -2s, which means add 4. Everything else remains unaffected. Boom. And at this stage, we've got our answer. We know that my x column, which came first, is 5, and my y column, which came second, is -2. So we solved the system. That's the point where these two lines cross, using Gaussian elimination. Awesome. So on number 21, I want you to go ahead and try this one. Pause the video, unpause it when you're done, and see how well you did. Go ahead and give this a shot from start to finish. Okay, so let's see how well we did here. I'm gonna go ahead and create my matrix and say this is gonna be an 8, 5, 7, 1, 94, 25. Ooh, this looks like we're dealing with some bigger numbers. I have my diagonal line. I'm addressing the 8 first, which means that row 1, the reciprocal of 8 is 1/8 of row 1. 1/8 of 8 is 1. 1/8 of 7, we get our first, not quite hiccup, but it's going to be 7/8. And then 1/8 of 94. Well, let's see, 94, we're going to kind of cheat here, and we're going to reduce this fraction as best we can. Is 4/47. Actually, let's go ahead and let's just leave it as 94/8. Most of these should sort themselves out in the end. So let's leave it as a 94/8. We know we can reduce it to 47/4. I think I typed that in upside down in the calculator, but let's see where this takes us. We're not going to touch anything. We're just going to leave it as it is. Cool. So I'm going to go ahead and take my diagonal. First thing I need to get rid of is the 5. So row 2 is going to be replaced with row 2 minus 5 of row 1. Ooh, so we've got some fractions and whole numbers working themselves in right here. Let's see how this does. Okay, so the first row is unchanged. 1 7/8, 94/8. Take away 5 1s. Take away 5 of these, which means we're taking away, let's see, 35 and 7. And so now what I'm going to do is just to hold my values in here. Okay, so I know 1 in terms of 8 is I have 8. And I'm taking away 5 of the numerator. So 8/8 minus 5 of the 7/8 is going to lead me to a -27/8. And I'm going to do the same thing right here. So 25 times 8, I'm going to have 200 in my numerator. So 200 minus 5 of the 94s. So I'm just looking at my numerators. Is going to give me -270. Does that divide by 8? No. So I'm just going to leave it as -270/8. Okay. So at this point, you're probably second guessing yourself and saying, okay, this looks very different than what we've done before. But take a look at our next step. Both these fractions are over 8. What we can do right here is say, hey, how do I reduce this step? Well, remember, when we reduce, we just multiply by the reciprocal. So row 2 is going to be negative 8/27 of row 2. The 8 on the numerator and the denominator is going to cancel both of these fractions out. So that's going to give us negative 8/27 of 0. Negative 8/27 of negative 27/8 is 1. And then lo and behold, the 8s are going to cancel out, and that's 270 divided by 27. So that's going to leave us with negative 10. Positive 10, actually. Boom. And so albeit it got a little messy there in the middle, when we go ahead and do the reduce step, it makes everything nice and neat. Awesome. And so our last step right here, boom, we're going to go ahead and cancel out that top value, 7/8. So row 1 is going to be row 1 minus 7/8 of row 2. The nice thing about leading these pivots into 1 is it's just whatever that value is of the pivot. We don't really care what else is going on. So minus 7/8 of 0, minus 7/8 of 1. Everything else remains unaffected. Okay. And we're taking away 7/8 of 10. So let's go ahead and bust this one out. So if I'm dealing with 94/8 minus 7/8 of 10, realistically what we're looking at if we only care about the numerators, well, 10 in eighths is going to be 80. So I'm taking away 7/8 of that. Actually, I don't even need to worry about that at all. Let's just take our 94 minus 7/8 of 10. 3. Boom. So you can see, even if they get messy in the middle, oftentimes they'll work themselves out. Now, that is going to be a nuance of some of the work that we're going to be doing together here. That's not always the case. There is no reason why x and y always need to be whole numbers, but in these intro problems, try to set it up so that we get nice common situations dealing with that. Okay. And then to close things up, we've got some critical thinking and some challenge questions. Does the process change when we add more variables? Well, I think we've discussed that no, the process does not change when we add more variables. In fact, it remains quite literally the same. We deal with our diagonal, and we go ahead and we reduce them. When we had rows of 4, we looked at our diagonal and we reduced the same amount. It just means there's more steps.